steam at 200 pound force per square inch and 600 degrees Fahrenheit, which is state 1, enters a turbine through a 3-inch diameter pipe with a velocity of 10 feet per second. The exhaust from the turbine is carried through a 10-inch diameter pipe is at 5 pound force per square inch and 200 degrees Fahrenheit, which is state 2. What is the power output of the turbine, given at state 1? The enthalpy is 1322.6 British thermal unit per pound mass, and specific volume is 3.058 feet cubed per pound mass. Given at state 2, the enthalpy is 1148.6 British thermal unit per pound mass, and specific volume is 78.14 feet cubed per pound mass. You have the given values for state 1. You also have the given values for state 2. In this type of problem, if you don't know where to start, try calculating the area of each pipe. The area of a pipe is equal to pi times the pipe diameter squared divided by 4. Calculate the area of the pipe for both state 1 and state 2. Do dimensional analysis to get the area of the pipe for both state 1 and state 2 in units of feet squared in order to be consistent with units of other values in the problem. The mass flow of the steam is equal to the pipe area at state 1 times the velocity at state 1 divided by the specific volume at state 1. The mass flow of the steam is determined to be 0.1605 pound mass per second. The velocity at state 2 is equal to the mass flow of the steam times specific volume at state 2 divided by the pipe area at state 2. The velocity at state 2 is determined to be 22.99 feet per second. Starting with the equation, change in enthalpy plus change in velocity squared divided by 2 plus the acceleration of gravity times the change in elevation equals heat transferred plus work done on the system. Because there is no mention of either elevation or heat transfer, assume there is no change in elevation, and assume there is no heat transferred. For now, focus on the part of the equation which consists of change in velocity squared divided by 2. This is equal to velocity of state 2 squared minus velocity of state 1 squared divided by the product of 2 times the g-c conversion factor. Since British units are used, a g-c conversion factor is needed. The g-c conversion factor is 32.174 pound mass times feet divided by the product of pound force times second squared. Plug in the velocity values and solve for this part of the main equation. This value of the main equation is determined to be 6.6597 pound force times feet divided by pound mass. Use dimensional analysis to change this value to units of British thermal units per pound mass to have consistent units with the enthalpy values. Dimensional analysis results in the value of 0.008558 British thermal units per pound mass. This is the value for the change in velocity squared divided by 2 in the main equation. The change in enthalpy is equal to the enthalpy of state 2 minus the enthalpy of state 1. The change in enthalpy is determined to be negative 174.0 British thermal units per pound mass. All values of the left side of the equation are determined, and the sum of the left side of the equation equals the amount of work on the system. The work on the system is negative 173.99 British thermal units per pound mass. Because the value is negative, work is being done by the system. In this case, it is the turbine. The power for the turbine equals the negative of the work on the system times the mass flow of the steam. The power produced by the turbine is 27.925 British thermal units per second. Using dimensional analysis, the power output of the turbine is determined to be 39.51 horsepower. This is the final answer for this problem. Great job! You are improving your understanding of thermodynamics. If you like this video, please subscribe, like, comment, and share. Subscribing helps out a lot and is greatly appreciated. If you missed something in this problem, please re-watch this video. If you have any recommendations for future videos, please leave a comment. Please check out other videos on this channel. Thank you for watching.